Mercado.
And I'm Yabusaki.
So here's the agenda for today. First, we'll start with a quick overview and some background information regarding Nicaragua. After that, we'll discuss some of the pressing issues that are currently in Sabana Grande. Then we'll introduce our design. After that, we'll give an overall cost of the design. Then we'll go into some non-technical issues. We'll conclude our presentation, and then after that, we'll take some room and we have some questions. So a little background information on Nicaragua. It is located in Central America, right in between Costa Rica and Honduras. It is the largest country in that region. But even though it's the largest country, it is considered to be the second poorest in the Western Hemisphere, with Haiti being number 1. 45% of the population lives below $1 a day, and the GDP per capita in that country is around $2,800, whereas compared to here in the U.S., it's around $46,000. El Proyecto, Sabana Grande is a community, and inside the community is a housing development of around 45 homes, which we visited. It's located 155 miles to the north of the capital, Managua. Approximately 200 people are currently reside in that community, and the average income is $2.50 a day. Thanks to with the help of the engineering here at Santa Clara, 4 of the 5 members were able to visit this community, and with our guide for our visit, Susan Kina, she was a guide. She's also the director of Grupo Phoenix. They're in charge of researching, developing, and adequately adapting sustainable energy in Nicaragua in order to increase the technical level of the local people as well as improve living and health standards. So our visit started landing here in Managua and taking a very long and uncomfortable 4-hour bus ride here. Each one of us stayed with different families where we got to enjoy some of their amazing cooking and coffee that they had to offer. But above all, we got the chance to interact with the people there in order to learn more about the culture and see how they actually live. So in el proyecto, the women do the usual household chores. They cook, they clean, and they make about 10 to 15 trips to a well that's about 50 feet away from the house, carrying 40-pound buckets. But they're getting more involved with the solar center, and they actually built a facility in that center with their own bare hands. The men work in agriculture, and they usually help out with construction projects. Here's the layout of the El Proyecto. Each one of the white boxes represents a house. Currently, there's 2 wells in that community, the lower end and the upper end. The one in the upper end actually has a washing facility and 2 shower stalls, whereas the one in the bottom, it does not. It's a fairly new system. It's around 8 years old. It was a gift from the Spanish government, and we actually tested the water quality, and we found that it was pretty adequate. So our trip was not a vacation whatsoever. We actually did some data collecting. We recorded some of the several observations as listed above. We got the chance to interact with the families and survey them in order to get a better idea of what they wanted and what they preferred from our design. We got to visit the city of Totogalpa, the city hall in Totogalpa, in order to get the plans of El Proyecto in order to get more information of the topography. After that, we determined our final project.
So now we will be defining the problem. When we went to Nicaragua, we arrived with the mindset that we were going to be designing for our original project, which was a comprehensive water distribution system. However, after learning more about the community, we realized that having to jalar, as they call it, or collect the water was their means of regulating water use. We also noticed that there were bigger issues at hand, like health and sanitation. And becoming engineers with a mission, like Santa Clara has taught us, we decided to modify our project to address the needs of the community and to see what fits them. So for the project school, we divided it into 3 separate sections. The first one is double composting the trains. The second is a water efficiency facility, and the third is an anaerobic biodigester. So as you can see on the drawing, our water efficiency facility will be located over in well 1. The double composting latrines are all the little blue boxes you can see next to the white boxes, and our biodigester will be located near the volunteer kitchen in the agricultural section.
So let's get into our first component of our project. I was in charge of designing the double pit composting latrines. So one of the most prominent issues in this community was that their lack of a sanitation system. They use a single pit latrine, which resembles a portable restroom, but there's a 6-foot hole in the ground where the solid waste accumulates. And in this presentation, I will refer as the fecal matter as solid waste. So once the solid waste is fills up that hole, they simply cover it and move the latrine elsewhere in their backyards. So what's wrong with this picture is that these families have relatively small backyards and eventually they will run out of space. Also, when talking to the families during our surveys, they all wanted something a little bit better in terms of reducing the amount of odors and the flies. And maybe perhaps something a little bit more aesthetically pleasing as well. So here are just a few of the types of latrines and other sanitation systems I took into account when I was in my preliminary design process. The ventilated improved pit latrine is actually what they have now. There is a single pit composting latrine with a bucket method that uses the most amount of maintenance. And there's multiple configurations of a double pit composting latrine. Like shown in this photo, there is one with both pits below ground and one mobile structure. And there's also types of latrines that are one superstructure that remains permanent and the pits are above ground. So my strategy in order to design this type of latrine is that I wanted to take into account all the existing conditions, what are the family's needs and their wants, and the amount of maintenance each latrine would need. So with that said, I decided to use an above ground double pit compost latrine with a permanent superstructure, so that way you never have to move it. And then the field survey data that I collected there during our visit was that the average use of the latrine was about once a day for solid waste only, and the average people per home was 4.5. Then I was able to research the type of data that they needed in order to calculate the required volume, such as the composting period is about 9 months, and this takes into account the climate in the area. The solids accumulation rate is about 2.5 cubic feet per person per year, and here's the calculation that I used in order to define the size of one composting pit. Notice that I did multiply it by 4 because one pit cannot exceed 3/4 full of solid waste, and this is due to that we have to take into account the amount of bulking agents that have to go in the latrine in order for the solid waste to compost. And I'll go into further detail about the bulking agents later in the presentation. So luckily during our visit in Nicaragua, they were in the middle of constructing their first experimental composting latrine, and this was good so I can see what kind of materials they have local and they're available to them, and the types of construction methods they used. In my design, it is slightly larger than the one they have now, and this is because I used a different composting period as well as a more conservative accumulation rate. Mine's about 7 feet long and 4 feet wide, and then there will be a concrete wall in the middle severing both the concrete pits. Here is the front view, the skeleton view of my composting latrine, and the concrete base is going to be reinforced with number 3 rebar, and about 2 feet high from the ground, and the superstructure is about 6.5 feet. And here is the side view. And then on the back wall of the latrine, I am going to incorporate a urinal just to give the men a little bit more space, because that's one of the things they told us during the survey is that they feel uncomfortable in latrines due to the amount of limited spacing that they have. And there will be a pit entrance on each side of the latrine in order to take out the compost once it's ready. Here's also a double pit composting latrine toilet where the urine is going to be diverted away from the pits. And they do have a mason there that can construct these types of toilets, and he's willing to show the community how to do that as well. So the operations of a double pit compost latrine is pretty easy. One family will use one toilet at a time, and once that first pit gets 3/4 full of the compost, or the solid waste, then they seal it off and they use the other toilet. Once the second toilet or the second pit is 3/4 full, then the first pit is now ready to be used as fertilizer and emptied out. And then they repeat this process over and over again. In order to properly maintain these types of latrines, a bulking agent must be inserted after each use, such as soil, wood ash, and lime. And I verified that these components will be available regularly throughout the entire year. And most importantly, that the education must be implemented for these double pit compost latrines. Luckily that they just finished building a community classroom where the community can come together, assemble, and manage where the compost is going to go, what types of plants and trees in their reforestation projects are going to use this nutrient-rich fertilizer.
Now we'll get into discussing our second component, which is the water efficiency facility that Agustine and myself designed. To give a little background, the El Proyecto is basically, if you think about it, is like an apartment complex in a rural setting. Very densely populated, like this room we have here. And there's limited resources, and it's an agricultural community. So this all combines to kind of a big issue with water conservation. So we need to come up with a viable solution that would provide a supplementary second source of water, and as well efficiently reuse the gray water that they produce. So what we came up with was a water efficiency facility as illustrated above in the rendering. There are several different components in the facility. The first is a rooftop rainwater catchment system. We based the design on 40 inches of rainfall annually, and it will have 515 square foot of roof, corrugated metal roof. This will supply 10,000 gallons of rainwater captured. As well, we will need a cistern to store most of the water during the peak flow periods. So it will be 2,920 gallons of storage, and it will contain a solar-powered pump. It will pump at 10-hour rate, 10 hours at 3.6 gallons per minute, and it will basically be a low-voltage pump because of the solar energy available, and it will be a 30-volt pump, which gives it 78 watts rated. Along with this, there will be a shower storage tank. One of the key aspects of what we noticed was most of the community actually showered early in the morning when there isn't much solar energy available. So it is crucial that they have enough stored during the nighttime so that when they wake up in the morning that they'll be able to take their showers. So we provide 100 gallons of rainwater storage, and it will be gravity fed to showers. And as well, there will be an overflow back to the sand filter, and the sand filter I'll discuss later. The overflow is because we'll be pumping continuously. As well, we'll provide a rooftop solar system to provide power to the pump. It will be at a 15-degree angle of tilt, and it will produce about, gives it the ability to have 5.8 kilowatt hours per meter squared per day of solar radiation. Based on the pumping needs, we knew that we needed 184 watts, and so we decided to design with two 120 watt panels. As well, the remainder of the components of the facility are 2 showers, and 2 wash tables. The showers will basically be using most of the rainwater captured. They'll need 180 gallons per day of shower use. And an ADA ramp, because we noticed that a few members in the community had accessibility disabilities. And so we based our dimensions on ADA standards, and as well as slow sand filter that will handle 2 to 3 gallons per minute and an overflow for any periods where the flow is greater. And we'll now get into more of the slow sand filter, which we actually were able to design and with help of Dr. Chiesa, and actually make a little model of it. So basically, this is the overall design of the filter. What ends up happening is as the water fills up to the almost overflow funnel level, it pushes the water through these 1/4 inch perforations, all the way up to 3/4 inch PVC, through the 90-degree connector, and through the T down to the 1 inch PVC. Any water that is above and beyond the flow rate that this can handle will go through the overflow. So, but the good news is that with rooftop rainwater catchment, most of the dirty, contaminated water is within the first few gallons of rainwater flush. So most of the water will actually get filtered, and then the rest, the clean water, will go through the top. As well, because of our pumping is continuously pumping, and it goes through the shower, through the overflow, back to the filter, the water will at least get filtered once a day. So there shouldn't be any issues with contamination. And here's a 3D rendering of the building itself. Here's a little layout. As you see, most of the components I talked about before. And one thing to note is all the gray water captured will go to a mound system through a main line, and Agustine will talk about